This is a canon from the musical Offering by J.S. Bach. The two violins are playing the same melody, except that the second violin is delayed by one measure relative to the first. Thus, the relationship between the two violin parts is really just the relationship between the violin part and itself at different times. Similarly, with random processes, we often study the covariance between a random process and itself at different times. The function that describes this covariance is called the autocovariance. The prefix auto comes from the Greek word for self. Just as an autopilot pilots by itself, or an autobiography is a biography written by oneself, the autocovariance is just the covariance of a random process with itself. So far, we have learned two functions for describing a random process. The mean function, which tells us for any time t the expected value of the process at that time, and the variance function, which tells us for any time t the variance of the process at that time. Today, we'll introduce a new function, the autocovariance function, which is actually a function of two times, s and t, and it tells us the covariance between the process at time s and the process at time t. Now, some people call the autocovariance function just the covariance function, but I like the prefix auto because it reminds us that this is actually the covariance between the same random process x at two different times, rather than the covariance between two different things entirely. Now, before we actually get to how to calculate the autocovariance function, I wanted to draw your attention to a fact that I hope you've noticed already. The variance function, v of t, can be calculated from the autocovariance function. That's because the variance function tells us the variance of the process in time t, but the variance of a random variable is just the covariance of that random variable with itself. In other words, the covariance between the random process at times t and t. So the variance function, v of t, is just the autocovariance function at times t and t. Now, let's work out the autocovariance function for a random process. Let's say this random amplitude process, where we first generate a from an exponential distribution, and then obtain a random function of time as a times cosine of 2 pi t. What is the autocovariance function of this process? First, let's write out the definition of this process. So x at time s is just a times cosine of 2 pi s. X at time t is a times cosine of 2 pi t. Now remember that s and t are just players to be named later. Once we plug in numbers for s and t, cosine of 2 pi s and cosine of 2 pi t will just be constants. So we can pull them outside the covariance, and we're just left with the covariance of a with itself, which is the variance of a. We know that the variance of this exponential distribution is 1 over lambda squared, so it's 1 over 1.6 squared, and we have our autocovariance function. It's a function of two times, s and t, and it's equal to 1 over 1.6 squared times cosine 2 pi s times cosine 2 pi t. Now, unlike the mean and variance functions, which we were able to visualize on this graph, because they are just functions of t, it is difficult to graph this autocovariance function on this same graph, because it is actually a function of two times, s and t. Now, this video is only focused on how to calculate the autocovariance function, but you will do a follow-up activity that will hopefully help you visualize this autocovariance function intuitively. Let's also calculate the autocovariance function for a discrete time process, the Bernoulli process. The Bernoulli process is very simple. At each time step n, we observe an independent Bernoulli p random variable. Now remember that Bernoulli random variables only take on the values 0 and 1, so two realizations of this process might look like this and this. Now, how do we obtain a formula for the autocovariance function of this process? Now remember, the autocovariance function is the covariance between the process at two times, which we'll call m and n. Now, in this case, we don't have a formula for x of n that we can just plug in here. We actually have to think about what the covariance is using the definition of the process, using what we know about its properties. So first, let's take two distinct times m and n, so where m is not equal to n. What is the covariance between x at time m and x at time n? Well, by the definition of the process, these two random variables are independent. So their covariance must be 0. Now, there's just one case we haven't handled, the case where m equals n, where x of m and x of n are the same random variable. Now, the covariance between any random variable and itself is just the variance of that random variable. And we know that each x of n is a Bernoulli p random variable, and we know that the variance of a Bernoulli p distribution is p times 1 minus p. So this is a complete answer to the question, what is the autocovariance function of a Bernoulli process? But I want to point out that there's a more compact way to express this autocovariance function. We can write this expression more simply as p times 1 minus p times a discrete delta function at m minus n. This discrete delta function is 0 everywhere except when its argument is 0. In other words, when m equals n. When m equals n, the delta function has a value of 1, which gets multiplied by p times 1 minus p, which is exactly this case here. And when m is not equal to n, this delta function is 0, so this whole expression is 0, which matches this case here.